NASA's Hurricane and Severe Storm Sentinel mission, or HS-3, completed 3 years of airborne measurements over tropical storms in the Atlantic to look at the processes that contribute to hurricane formation and intensity change. NASA's Global Hawk unmanned aerial vehicles and the high-flying WB-57 flew 6 instruments above and around tropical storms to study the role of strong thunderstorms within them and the large-scale environment surrounding them.
We have done 3 deployments at the Wallops Flight Facility. It's been kind of quiet seasons in 2012, 2013, and 2014, but we've actually overflown a lot of tropical storms, and it's because of the range of the Global Hawk.
HS-3 flew more than 600 flight hours during the campaign, with 21 flights over 9 named storms.
I think we've shown over the 3 years with the cases that we've had that the Global Hawk platform provides a terrific way to get measurements over storms, to sample the large-scale environments, to get repeated observations within the inner core. We can map out the evolution of the storm over a large segment of its life cycle in ways that just haven't been possible in the past.
HS-3's meteorological and remote sensing instruments collected detailed vertical profiles of cloud structure, temperature, pressure, winds, rainfall, and humidity. One instrument called AVAPS, the Advanced Vertical Atmospheric Profiling System, released more than 1,400 weather transmitters called dropsondes during the HS-3 campaign, providing unprecedented coverage both inside and outside tropical storms and hurricanes.
The sun has left the aircraft. The sun has left the aircraft.
One of the overarching scientific goals of HS-3 was to study the role of deep convection in hurricane intensification. There has been a fair amount of debate about, is it really deep convection that causes intensification, or is it more of a result of intensification? So looking at the radar coupled with these dropsonde measurements, we're really getting a more solid understanding of what the structures of this convection is, how it feeds back onto the hurricane as a whole. And so we're getting more confidence, I think, that this deep convection does play an important role in actually causing intensification.
Another question behind tropical storm formation and intensity change is the impact of hot, dry, dusty air that drifts into the Atlantic from Africa's Sahara Desert. There is much debate about the role of the Saharan air layer, or SAL, and whether it contributes to or suppresses storm development. One of the longest-lasting hurricanes on record that was studied during HS-3 may provide some valuable insights.
Hurricane Nadine in 2012 was our best example of the interaction of the Saharan air layer, or SAL, with a tropical cyclone. In the Nadine case, we saw a major outbreak of Saharan air in the storm's environment. One of the things that we saw in the observations was that the dust was sort of being kept at bay outside of the outermost rain band of the storm. We saw some evidence that perhaps, even though the dust wasn't affecting the intensity of the storm all that much, it might have impacted the size of the storm, where the storm was smaller in the case with dust and without. With some additional simulations, I think we'll be able to come up with a much clearer answer.
The 2014 Atlantic hurricane season turned out to be the best deployment year for HS-3, with 4 storms, 2 of which became major hurricanes.
This 2014 season, we collected some data that is allowing us an unprecedented look at the early stage of what we call secondary eye walls, and they have been long believed to kind of be a pathway by which the inner eye wall can decay, and the outer eye wall will basically grow and replace the inner eye wall. Well, we have some new data of what the wind structure and the thermodynamic structure is during that early formation of that outer eye wall. It's very exciting because we have a theory that we've developed to characterize and understand and even predict certain features of this process.
One of the things that we've done as part of HS-3 that was done only in a very limited sense prior to HS-3 was looking at the structure of the outflow layer in tropical cyclones. That area where it spreads out in the upper troposphere has seldom been observed except by a few aircraft like the NOAA G4. So the Global Hawk, flying above the storms, allows us to sample storms from the lower stratosphere above the storm all the way through the outflow layer and down to the surface. And with the high resolution information we're getting from the dropsondes, coupled with the very detailed cloud measurements that we get from the cloud physics LiDAR, we're able to connect what we're seeing from the dropsondes to that CPL structure and understand how cloud structure relates to, say, vertical variations in temperature and humidity or wind shear in ways that hasn't really been possible in the past.
It was a challenging set of years in terms of just the storms that were available. We didn't really have a lot of these classic Atlantic tropical cyclone, major hurricane developments. Edward was one of them. Certainly Hurricane Nadine from a couple years ago was surprising for how long that it lasted. And so there's been a lot of research looking at the processes that really help to sustain Nadine and but prevent it from becoming too strong. So every storm we fly, there's always something unique about it, and that's what makes this job so exciting. So we're really fortunate to have the kinds of data that we can get from HS3.
Well, I think the most important thing is that we've learned a new way of looking at hurricanes. We're looking at hurricanes with a platform that can fly over hurricanes and stay on it for an extended period of time over at huge distances from the United States coast, or stay on it for a long time as it approaches the coastline. So this is a new asset, it's a new way of doing science, and I think we're going to see a lot of this in the future.